Alrighty, so here we are with the last topic, test for differences between two population proportions. Let me go straight to the two-tailed test. Suppose someone tells us that there's no difference between one population proportion and the other population proportion, so when we subtract one from the other, we get 0. And we're like, I think those two are different, or I don't trust you, or let me just not necessarily be argumentative, let me just set up a good scientific test to see if I can find overwhelming evidence that in fact there is a difference. So maybe someone says, all right, the proportion of men who support Donald Trump is the same as proportion of women who support Donald Trump. So in that case, the proportion of men minus the proportion of women would be 0, or close to 0. And we would set up an alternative hypothesis, which would be the opposite of that. The proportion of men minus proportion of women would be not 0. There are two ways we could disprove this null hypothesis if we find a really high positive number or a really high negative number. So that would be a two-tailed test. If we were looking to prove or disprove something a little more specific, if someone maybe said, hey, I think the proportion of men who support Donald Trump is significantly greater than the percentage of women who support Donald Trump. So if we take proportion men who support Donald Trump minus proportion women who support Donald Trump, we're going to get a number greater than 0. It's going to be a positive number. So we would set up a hypothesis, null hypothesis, with the opposite of that. We would say proportion of men minus proportion of women is either 0 or less than 0. And if we find overwhelming evidence that this is positive, then we could reject the null hypothesis and assume the alternative hypothesis. So in that case, if we're trying to say something specific, prove something specific, we could use the one-tail test. If we're trying to say or prove the other direction, we could use a one-tailed test, the other side. And then as I started saying, if we didn't know, or we didn't want to get specific in our first question, we would leave open the possibility that we could disprove the null hypothesis either with a really high positive or really high negative number. So everything is the same as with all the other hypothesis testing. We can use a critical value approach. For the difference between two population proportions, we use the z-distribution. We're good with that. And if our test statistic is outside the critical value, then we reject. We could also use the p-value approach. We'll get our test statistic. We'll see the area under the curve associated with that test statistic. For a two-tailed test, we'll double it. For a one-tailed test, we will not double it. And we will reject if the p-value is lower than our significance level. All right. So the key to all of this, as you might have guessed, is the sampling distribution of sample proportion differences. So this is a proportion difference. All right. This is proportion of men who support Donald Trump. This is proportion of women who support Donald Trump. If we were to do that same sample 10,000 times, we put it on this distribution, it comes out to this beautiful bell curve. The mean of that distribution is the actual difference. Like maybe it's 6%. Maybe in reality 6% more men support Donald Trump than women support Donald Trump. That would be the mean and would have a standard deviation based on how close these proportions are to 50%. Yes. It would have a standard deviation that statisticians have used or constructed for us when we're combining two populations. Okay, and this distribution is normal as long as we use good sampling size, and the standard deviation is, as we learned a couple classes ago, this formula right here. All right. And we're going to use the same principles, the same Rejection, same don't reject type of thing. This would be a one-tailed test with 5% of the data in the upper tail. We would say, well, if there truly is no difference between proportion 1 and proportion 2, then we would only get a sample proportion difference this great, this significant 5% of the time. Same thing. If the null hypothesis is true, then this would only happen 5% of the time. And when I say this, I mean the sample proportions that we go out and test using good sampling techniques, and we find the difference between those two. Alrighty. And then we're going to get our test statistic. It's the same subtract 0 principle here. We're going to say our sample proportion 1 minus sample proportion 2. So we go out and we sample men, say, do you like Donald Trump? We go out and sample women, say, do you like Donald Trump? And we find a difference. We find the difference of men is 6% greater. So 6% is the difference. And we subtract 0 because we're using a no difference question. Just as I mentioned in earlier examples, we could put something other than 0 in, and we could test. We could say, you know what, I think the difference is exactly 4%. And I'm going to test to see if that's true, in which case I would subtract off 4 and see how far off I am. But for now, we're just taking the difference, assuming no difference, so we're subtracting off 0. So sorry if that gets a little confusing. We're first taking the difference between the sample proportions, and then we're saying, well, if we're going to do a no difference hypothesis, then we subtract off 0, and we simply see how many standard deviations this proportion difference is above the mean. So we divide by the standard deviation of the sampling distribution of sample proportion differences. And I believe on the next slide, this part, the standard error is filled out a little bit more. Or no, it's not. Okay, so we don't have it. We had this in the previous slide. It's that big long formula. Just make a note of it. Turn back to the previous slide, say star. That's the formula we're going to need to use when we calculate the standard error. The thing I need to talk about now is what we use for the standard error. When we're calculating this standard error, I guess we do have it. We have it down here. This is the standard deviation for the sampling distribution of the sample proportion differences. And you will see we've got this sample proportion pooled here. What that means is we are going to combine the proportions we get for the two samples. So if we take the proportion of men who support Donald Trump, we take the proportion of women who support Donald Trump, and we do a weighted average of those. And that's going to be our pooled sample proportion that is going to help us find the standard error. And one above here, this formula here is just a weighted average formula. So, all right, number of men we ask times the number of men who support Donald Trump plus number of women we ask times the percentage of women who support Donald Trump divided by the total number of people we asked is going to give us our weighted average for sample proportion. So that's a little nuance that may trip you up. You're going to need to calculate the weighted average for the two sample proportions when you're calculating the standard error. One more time, you're going to need to calculate the weighted average of the two sample proportions when you are calculating the standard error. All right, if we're in class, I would say ask if there's any questions, but I'm going to assume there's not. And we are going to do an example to make sure we're clear on this. Page 373, number 38.